All right, so we're continuing our discussions with Thomas Möllenhoff on Sharpness-Aware Minimization. Looking forward to your talk.
Yeah, thank you for the kind introduction and for organizing this fantastic workshop. Yeah, today I want to talk about the beautiful connection MT and I discovered between a recent method called Sharpness-Aware Minimization and Approximate Bayesian Inference. So I don't think I need to talk a lot about this, but yeah, as we all know, we've witnessed quite a deep learning revolution over the last decade. And we have seen all these amazing applications. So does it mean that AGI is solved? But yeah, as we've seen yesterday, there's plenty of failures in deep learning. For example, some state-of-the-art image detector thinks that we have here a cow which is 5 meters long. Yeah, we have these adversarial examples that we've seen yesterday. We add a little bit of perturbation to a duck and it becomes a horse. Companies which try to use deep learning to build self-driving cars, they experience catastrophic failures. And recently we've seen a human amateur beating the top Go playing AI using a simple trick. So we are far away from having a stable and robust technology, and it's quite dangerous actually as it's being deployed in the real world now. And so over the last 2 years, my research has been focused on improving deep learning and fixing these failures using ideas from Bayesian statistics. And today I want to give you an example of this research program. So we will see how a very popular deep learning method, this Sharpness-Aware Minimization approach, can be interpreted from this Bayesian perspective. And we will not only see this beautiful connection, but we will also see how we can use this connection to further improve the deep learning methods. So let me start talking about what I mean by this Sharpness-Aware Minimization method. It was proposed independently by 3 different research groups, actually. But people call it now SAM, Sharpness-Aware Minimization. And it has been very, very influential in deep learning. So it was proposed 2020 and it's cited 500 times. And what does this method do? It's basically you change your training method and you get improved test accuracy across all sorts of models. And it not only improves your test accuracy, it also improves robustness, calibration, interpretability, transfer learning, compressibility, federated learning. So there's a bunch of other papers just coming out all the time. Sharpness-Aware Minimization improves XYZ in that application. So seems to be quite a magical method. And what does it do? How does it work? It's actually quite simple. So the principle behind Sharpness-Aware Minimization is that of adversarial weight perturbation. Yesterday, we've seen quite a lot of methods which perturb your input data to get a robust network, which is not sensitive to input perturbations. Here, we perturb our parameter vector theta. So these are the weights of our neural network. And we don't optimize our loss, but we perturb our loss with some epsilon. And this epsilon is in a ball of radius rho. So rho is a hyperparameter. It's searched with graduate student descent. And we kind of search for the worst case loss in that ball. Then we try to minimize this worst case loss. And they came up with some approximate method to solve this loss, and it gave these great results. But the big question, of course, is why does that method work? How can we improve it? And so on. So one hypothesis that the researchers, why they developed this method is the hypothesis that in deep learning, it's a non-convex problem. So you have lots of different minima. And then the question is, which minima should you pick? And there's some evidence that you want to go to a flat minimum in your high-dimensional loss landscape. So you prefer to sit in the middle of this guy rather than going to the sharp minimum. And so there's empirical and theoretical results that suggest that we should try to find these flat minima. And lots of these arguments, they rely on Bayesian viewpoints. And but precise connections between the Sharpness-Aware Minimization and Bayes has been missing until now. And our work aims to fill this. So let me introduce the Variational Bayesian approach, which has also a bias towards flat minima. So in typical empirical risk minimization, maybe you just minimize your loss function, find your optimal parameter with your favorite optimizer, maybe stochastic gradient descent. In the Bayesian approach, we say, okay, we don't know which is our optimal parameter. So why not search for more than one? For example, you could search for a Gaussian distribution over the parameter space. And then we want all our experts, which we collect in our Gaussian distribution. If we draw a random parameter vector from that Gaussian, we wanted to have low loss. And if we would just optimize that first term, we would concentrate to a kind of Dirac measure. So we add some kind of regularization, some smoothing. We've also seen this yesterday to prevent our distribution from collapsing to a single point. And so why does this have a bias towards flat minima? So I plot here for a very simple Gaussian approximation. I plot here this expectation of the loss for a simple one-dimensional non-convex loss landscape. And as we increase the variance of our posterior distribution, we get a smoothed version of our loss. And if the variance is large enough, we can, if we would optimize the red loss, we would go here to the flat minimum. So this first term in our variational Bayesian approach, it smooths the loss by averaging over weight perturbations. So it can be rewritten in the following way. We have some, so this is done by just pulling the mean as a perturbation with this plus epsilon. And this looks like a similar mechanism to the SAM approach, but it's using the expected loss instead of the maximum loss. And an advantage of this Bayesian formulation is that this parameter sigma, which is picked by hand in SAM, it can be actually estimated by optimizing the subjective. That's one advantage of this formulation. So we have two similar looking things. We have the SAM loss, which considers only the worst case perturbation. We have the Bayesian approach, which rather than looking at the maximum inside some ball, it picks a random sample from our posterior distribution and averages many of these random samples. So we average over multiple perturbations. So these look somehow related, like the rho could be loosely associated with the sigma square, but there's no precise connection. And what we found in our work is a very surprising connection between these two through an object called the Fenchel biconjugate. So this is a kind of a way to compute optimal convex relaxations. This is what I will explain in the rest of the talk. You will see how we can go from the maximum loss to this, from the expected loss to this maximum loss using this idea of the Fenchel biconjugate. So this, the details are in this paper here. If you want, it's on archive. And yeah, so we will see that this SAM loss function, it's equivalent to minimizing an upper bound to this expected loss that we've seen with respect to mean while keeping the variance fixed. So I've plotted this here on this one-dimensional cost function. The expected loss is the blue curve, and the upper bound obtained using SAM is the red curve. And if we optimize in this distribution space, it kind of corresponds to a lifting to this higher dimensional, two-dimensional space, where these slices, as we increase our variance, they correspond to more and more smoothed versions of the loss. And we will see that SAM is equivalent to optimizing a certain upper bound to this expected loss. It turns out to be, in some sense, an optimal upper bound. And how did we obtain this upper bound in practice? We obtained it using a tool called the Legendre-Fenchel Transform. And the main idea of this Fenchel transform is to represent a convex set as an intersection of half spaces. So as you can see, for convex sets, you can always kind of intersect them, support them with half spaces, and we get a dual representation of our convex function. For non-convex functions, this is not possible because these kind of linear supporting hyperplanes, they cannot go inside the dent in the function. So this Legendre-Fenchel transform, it basically, it tells you how much you can push your linear function up until you hit the graph of your function. And then once one has this Fenchel conjugate available, one can get a dual representation of the function f in terms of hyperplanes. So we maximize here over the slope of the hyperplane, and the conjugate tells us how much can we push this hyperplane up until we hit the graph. So we have f star star, which is the optimal convex lower bound of our function f. And yeah, it's obtained using this Fenchel transform. So it turns out that the Sharpness-Aware Minimization loss, it can be derived by computing the Fenchel biconjugate of the expected loss. And for that, it's very important to work in a very specific parameterization. So we don't work in the typical mean variance parameterization of our Gaussian, but we work in the moments of the distribution. So the first moment is just the mean. Second moment is the square of the mean plus the variance. Here our favorite example of this one-dimensional loss. And this is how our construction looks like. So the blue surface here, that's our expected loss, expected negative loss, because we want upper bounds. So we apply the Fenchel conjugate to the negative loss. And the red surface is this optimal convex lower bound of the blue surface. And then if you look at this, maybe your first thought is, how can this be convex? This was actually also the reviewers' comment. So many reviewers of this paper didn't understand that this is actually a convex function, the red surface. It looks quite weird. But the reason is this can be convex is because on the boundary, any point on the boundary here cannot be, it's not the convex combination of two other points on the boundary, because these are all extreme points of this convex set. So we can prescribe any convex, any non-convex function to this boundary of the set. And the convexification retains all the information of our original non-convex function. So this is a very specific construction, and for this parameterization is important. And only by taking the conjugate in this parameterization, we can obtain the SAM loss, as we will see now. Okay, so given this construction, what do we do now? We start with our Bayesian approach. We simply rewrite it. So nothing happened here. We just had here the negative expected loss. We rewrite it as minus the expected negative loss. Because the expectation is linear, we can just do this step. And now by doing this, we can plug in our optimal convex lower bound, which will give us an optimal concave upper bound to our Bayesian problem. So this is a way to construct the bound. And it turns out that this is a difference of convex functions. So this is convex with a minus, and the KL for Gaussian distributions or exponential families, it's also convex. And for these difference of convex type problems, there's always a dual problem. So we can write this problem in an equivalent dual way. And it turns out, so I don't have the time to go into the details here, but if we consider an isotropic Gaussian prior and posterior approximation, then this dual objective here, f star of lambda minus g star of lambda, if we reparameterize that in the mean and the standard deviation of our Gaussian distribution, we recover the maximum loss. So the expectation is gone. So to summarize, we have our Sharpness-Aware Minimization objective, and we have our optimal relaxation of the Bayesian objective, and they look almost the same. So we can recover the SAM objective from an optimal relaxation. And very interestingly, the variance of our posterior approximation, so the sigma square, it plays the same role as the hyperparameter rho in SAM. So it controls how strong our adversarial perturbation should be. The only difference is in our convex relaxation of the Bayesian objective, we get a soft penalization on the epsilon, whereas the SAM people, they decided to give this trust region constraint. But it's well known in optimization that trust region and soft constraints, there's a equivalence under some assumptions. But this gives a very nice interpretation of the rho parameter, and the Bayesian framework now offers us a possibility to also learn this parameter through the Bayesian objective. So we've seen the very surprising connection, or at least I found it surprising, between the Bayesian objective and the SAM objective. But now we can also use this theoretical insight to further improve SAM. So now we can actually learn the variance, this parameter, by just optimizing our relaxed Bayesian objective. And there's several ways to optimize such a cost function. The main challenge is here, of course, this biconjugate function. It's very hard to compute gradients of this biconjugate function. So here's a kind of an analytical expression for the biconjugate that we derive in the paper. And our learning algorithm is actually very simple. It's this is a difference of convex functions. So for alpha equals 1, this can actually be seen as a difference of convex algorithm on that objective function. And if we introduce here some damping parameter, this is something we call the Bayesian learning rule. And it basically takes your old posterior approximation and combines it with a convex combination with the new information that's arriving in through your gradients. And this gradient here of our biconjugate function can be computed by solving this optimization problem. So solving this optimization problem gives us a subgradient of this biconjugate function. So in every iteration of our algorithm, we have to solve this huge problem. And of course, this is quite hard. To arrive at a practical algorithm, we do some approximations. And so on the left here, I show what people do in practice in deep learning, what's proposed here in the Sharpness-Aware Minimization paper. They kind of have, for example, this RMS prop optimizer. And the only difference to normal gradient descent is that you don't evaluate your gradient at theta, but they evaluate the gradient at a perturb point. And if we kind of approximate here our difference of convex algorithm or Bayesian learning rule, if you approximate that with, you approximate the biconjugate computation with some tricks, similar tricks they do in this paper here, we arrive at a modified version of SAM, which we call Bayesian SAM, BSAM, and the differences are highlighted in red. So we introduce here some random sampling. We precondition the gradient not by the norm of the gradient, but by the scale vector. And maybe the main point of this algorithm is that this learns a probability distribution. So omega and S can be interpreted as the mean and the diagonal covariance of a probability distribution. So we don't learn a single model, but we learn an infinite collection of models, and we can sample random models. So this algorithm does variational inference, whereas this method doesn't have such an interpretation. Okay, so let's maybe go over the results. Our BSAM method, we first evaluated on some very simple toy classification problem, logistic regression problem, where this normal Sharpness-Aware minimization finds quite an overconfident decision boundary. And if we run our Bayesian method, we can find a solution which is more uncertain in regions where there is no data. They're similar to this exact Bayesian posterior, which we can analytically compute on this simple toy problem. We've also ran it on larger neural networks. Here, ResNet 20 on Cypher 10, Cypher 100, Tiny ImageNet. And we evaluated with respect to test accuracy, but also other metrics like negative log likelihood on the test data set, expected calibration error, this AU ROC. So these last two measures, they try to measure how well calibrated your network is. So how confident it is when it's correct, or how overconfident it is when it's wrong. So here, a smaller number is better. And we can see that this Bayesian SAM method, it consistently improves over SGD, but also over the SAM approach. So we got here quite good numerical results for our approach, which further improve over SAM. Also works on larger neural networks. So this is for neural network of 11 million parameters. We also got consistent improvements over SAM. But we can also see that this Sharpness original SAM method, it gives improved uncertainty over SGD. And we kind of offer an explanation for this because we see this method also as a Bayesian method in some sense. So it was not surprising to us that the SAM method also improves these quantities, not only the test accuracy. Okay, so let me maybe give one last experiment here. we've seen improvements, and of course, we wanted to understand why this BSAM method works so well in practice. So in the paper, we run some ablation studies. And one reason we could get good results is by using this Bayesian model averaging, because now we are learning a distribution rather than a single point estimate. We can sample random weights from the distribution that the BSAM method estimates. And then we can average the prediction of all these experts. So we can sample K experts from our estimated distribution. And we can see that by increasing the number of samples, our accuracy starts to increase and our calibration error decreases. Okay, so to go back to the original motivation, to improve deep learning methods using Bayesian principles, we've seen this Sharpness-Aware Minimization method, which really gives state-of-the-art results for deep learning. It's very popular. It appears similar to Variational Bayesian Inference, but there's a key difference. SAM uses worst-case perturbations. In Bayes, we average over many different perturbations. And we created a bridge between these two worlds using this Fenchel duality. And this bridge allowed us also to not only connect these methods and understand SAM better, but also to derive a new Bayesian SAM method. And this Bayesian SAM method improves SAM to obtain better uncertainty estimates. And sometimes it can also improve the test accuracy. So that's everything. Thanks a lot.
Okay, I also have a question. So thank you, Thomas. Maybe as time goes on, you become the Schmidt-Huber. I just would like to point out that in 2018, NeurIPS, we actually introduced this concept as an epsilon perturbation stability and did global optimization using Gaussian process prior. So maybe it is worth thinking about it. But from what I understand, the way you motivated SAM is that under your Gaussian reparameterization, it comes out maybe not exactly, but somewhat similarly to SAM, right? So you take your expectation over the distribution with this epsilon, and by applying double Fenchel conjugation, you have these additional terms. So it's not exactly SAM, but somewhat similar.
Yeah, this is the main difference: the soft constraint versus the hard constraint.
All right. In this particular case, then for the distributions over these parameters, have you looked into approaches that also looked into these kind of things using mixed Nash equilibrium ideas? Because you can also say that I have a minimax problem, but as opposed to learning a single parameter, I can try to learn distribution over these parameters. And that leads to these mixed Nash kind of algorithms that also carry out uncertainties and do sampling in order to get solutions.
Yeah, I'm familiar with the mixed Nash equilibrium work. I believe you applied it to GANs in one paper, but here we really wanted to make a kind of a precise connection to SAM, because this method is extremely popular in deep learning, so we wanted to somehow make the connection.
And the algorithm there is actually simple gradient descent ascent, and as opposed to writing it 2 lines, they want to compress it in 1 line, so they actually approximate gradient descent ascent in a weird way that is not provable.
Yes. They make very coarse approximations to this, and we make similar approximations to get our Bayesian SAM method.
Okay, thank you very much.
Thank you for the nice talk. So please correct me if I understand wrong. So I think your work, SAM, is to change the standard variational Bayesian inference, change from the expectation of loss to the worst case of loss by perturbation. And the perturbation is constrained by the variance, right?
Yes.
So it's similar to adversarial training. And in adversarial training, usually we do the perturbation on data and then minimize on the theta. Now you do the perturbation and the minimization same on the parameters.
Yes.
Is this no problem?
I mean, it's a different paradigm, basically. You say here, if you do the perturbation on your parameters, you're saying, I want some kind of I want to find a robust parameter. And
yeah, I mean, in the adversarial training, usually min max is for different variable. Max is for data perturbation.
Yes.
But minimization is for theta.
Yes.
But now you do the perturbation and the final minimization on theta simultaneously.
Yes.
Yeah.
So this was.
Yeah, I would like to understand.
What exactly do you like? Whether there exist convergence guarantees, or what exactly is the what understanding?
So on one side you maximize, and another side you minimize.
Yes.
But on the same thing, on the same parameters.
Yes.
Okay.
I mean, this was not proposed by me, but independently by these three groups here. And actually, in that NeurIPS 2020 paper, they do both. They do adversarial perturbation on the data and on the parameter. Okay. So that was one of the first works.
Okay, thanks.
Yes, okay. I will look into it.
I have two questions. One question is, when you derive your theory, do you assume the loss function is convex respect to the parameters?
No convexity assumption.
No convex, no such assumption.
No
okay. Then another question is, how do you manage the high dimension of the parameters? Seem you do not have the curse of dimensionality. For example, the network is so large, then will be also challenging for SAM and also Bayesian.
You mean if you really want to globally optimize this? Of course, if it's non-convex, if you want to find some kind of global solution, then you will suffer from the curse of dimensionality.
Yeah. The common problem. What do you
here
think?
We are happy with some kind of local solution, or even simpler, biasing the training trajectory towards a good minimum. So we're not interested in finding here global optimum.
Okay. So then there knows the dimensionality problem, you think?
Well, there would be if we want to find the global optimum, but in deep learning, it's hopeless, or maybe it's not hopeless, but it's not the goal. The goal is to bias ourselves maybe to a nice place in the loss land.
Yeah, because from my understanding, is if the dimensionality is low, random sampling will be enough to cover the flatness. For example, traditional Bayesian things. Now the network dimensionality is very high. That's why we need to have some directed, gradient to direct which part is the most vulnerable part, then flattened, then again and again, then it can make it flat. So yeah, then I guess
It's a very good comment. So actually, we were surprised also why this method works so much better than this one, because this is actually a lower bound. So this should be more faithful to the true Bayesian objective, but in practice it works worse. And as you said, this could be because here, if we want to optimize this objective, we have to solve a very high dimensional integral.
Yes.
High dimensional integration suffers from curse of dimensionality, and this could be seen as some kind of very cheap way to approximate this. This could be one reason for the success of SAM. And if you could faithfully solve this one, maybe you could get better results. But
yeah, this gives me the feeling that you actually solve the curse of dimensionality problem by linking these two together.
Yeah, maybe, yeah.
Just give me this strong feeling.
I mean, we don't have any theory, so it's more, I mean, we have the theory which connects these two, but we don't study certain convergence aspects.
This connection is super good. Yeah.
All right, let's thank Thomas for this.